Any questions from anything we've done so far? All right. My memory is we finished 4.1, and that's exactly where we stopped. We didn't get going in 4.2, or did we? I don't think we did. Okay. So, we're still in Chapter 4, Trigonometry, Measurement of Triangles, and 4.2, Trigonometric Functions based on the unit circle. What in the world does unit circle mean to you? Anything? What does unit mean? Any of you play that card game called that when you get to the last card you have to yell out something? Say again? It means one. Uno. Okay, unit. One. Unit circle is a circle of radius 1. Circle of radius 1. Okay? We didn't start on this last time? Okay, what we're going to do is identify a unit circle, describe its relationship to real numbers, okay, in a weird kind of way. We'll evaluate trigonometric functions using the unit circle. We'll use the domain and period to evaluate sine and cosine functions, and use a calculator to evaluate other trigonometric functions, well, including sine and cosine. So let's start with the unit circle. And as I just said, it's a circle of radius 1. Two historical perspectives of trigonometry incorporate different methods for introducing trigonometric functions. Back when I was, believe it or not, high school, that was just a millennium or so ago. So it was in the last millennium. Okay. We started off with triangles, and that made perfect sense to me. Then they introduced the unit circle, and you went, oh yeah, you can talk about them that way too. This book and most modern books, for some reason, start with the unit circle and then later do the triangles. And I have noticed that does cause students to make a certain type of error, which I think if you went the other way, you'd be less likely to make. But I'll try to warn you of that before it comes. So here's what we mean by a unit circle. It's a circle of radius 1, and a circle is written basically as x squared plus y squared is equal to r squared. And if the radius was 1, then r is 1, r squared would be 1. This is the definition of a unit circle. Every point on a unit circle will satisfy that equation. Oh, and this is a unit circle centered at the origin. Okay? Centered at the origin. Now, you see this point here, 1, 0. When x is 1, y is 0. 1 squared plus 0 squared is 1. And when you come up to this point, 0, 1. 0 squared plus 1 squared is 1. When you go over here to negative 1, 0. Negative 1 squared is 1 plus 0 is 1. And when you go down here, 0 plus negative 1 squared is 1 plus equal to 1. Okay, so certainly there. But every point in between, every point here, where this is just a tad less than 1, but this is a tad more than 1, then they satisfy this. Every point on that unit circle satisfies that equation. Okay? And we'll be calling on that in the near future. So hang on to the concept. Now, this is the part, and it's fine. It's a little bizarre, but it's basically what we're doing when we're talking about arc length. We're doing this very same thing. Now, though, they're wrapping the real number line around a circle. Not an arc length, but a real number line. Wrapping it around the circle, bending it just enough so it stays on that unit circle. With positive numbers corresponding to counterclockwise wrapping. Okay, I can't even talk, much less wrap. So, and negative numbers corresponding to clockwise wrapping. If you look down there, those would be negative. T's would be negative down there. Okay, and we know the angle is negative when you go clockwise, positive when you go counterclockwise. So basically, whatever angle you've got here to some length on that real number line that you've wrapped around the circle. Okay? You've actually made it part of the arc. Okay? So, every angle theta corresponds to one and only one, well, I'm going to say that, value on the real number line. Okay? And this is positive t's, negative t's. Just put your, it's sort of like you take your y-axis and put an axis just like it over here, so up is positive and down is negative. And maybe this is why counterclockwise winds up being positive, because you're wrapping the positive in the number line around. I don't know why. All right. Kind of makes sense? Okay. Now, as the real number line wraps around the unit circle, each real number t corresponds to each value xy on that circle. I was pointing out corresponding to the angle, but it's also corresponding, every value here corresponds to each little value on this unit circle is some number represented by that t, the bit t that goes around the circle, that real number line that wraps around. Okay? For example, the real number 0 corresponds, okay, now we talk about the angle style, but no, the real number 0 corresponds to the point 1, 0. Okay. Now, moreover, because the unit circle has a circumference of what? 2 pi, because 2 pi r is the formula for the circumference of the circles of radius r, and when the radius is always 1, this will be 2 pi. The real number 2 pi also corresponds to the point 1, 0. So every point has an infinite number of values on the real number line, but they're very specific ones. Every angle theta corresponds only to one point there. So we'll get back to that. Okay. We did all this earlier. Okay. In general, each real number t also corresponds to a central angle theta, that's what I was talking about in standard position, whose radian measure is also t, because remember, t was the arc length. I started off saying that. When you wrap that number line around, you're basically talking about arc length. So that radian measurement is that value t. Why? Because the radius is 1. Okay, so that's exactly the same. With that interpretation, remember here, S is equal to r theta. If r is 1, then the value for S is the same number as the radian. Okay? Now, a little bit of a problem here. S is a dimension quantity because it's in some sort of length quantity where theta has no dimensions. It's just the value of the same. The dimension comes from the r. That's one whatever. 1 centimeter, 1 inch, 1 mile, 1 furlong, 1 whatever. That has a unit with it, and therefore the S will have that same unit. But because this has a value of 1, the numerical value for theta of S will be the same. So it indicates the real number t is the directional length of the arc intercepted by the angle theta. That's what I was pointing out. I wasn't pointing out that t was the same as S, but indeed it is, when you have a radius of 1. All this is on the unit circle radius of 1. Whoa! That's all we have there. Now let's move to trigonometric functions. All right. From the preceding discussion, it follows that the coordinates x and y are two functions of the same real value variable t. So your x is some function of that t, your y is some function of the t. Okay? Now, you can use those coordinates to define 6 trigonometric functions of that same variable t. Now, there are times when I wonder why they even introduced the real variable t. Why don't you leave it theta? Because we just saw it's the same value there. And when I think of taking a trig function, I think of taking it of the angle theta rather than just some nebulous real value t. Because that T, in my mind, being a little more physical in my thinking process, Ryan's here, is that real value T has a link to it. And you don't take a trig function of anything with a dimension. You only take trig functions of dimensionless quantities. So I don't like to say it's a function of T. I like to say it's a function of theta, and theta has the same value as T, just without any dimensions in it. But that's me. Okay. Now, here's how they list them, and I think this is a weird way of listing them. I know why they're listing them this way, but when I think of the 6 trig functions, I think sine, cosine, tangent, cotangent, secant, and cosecant. That's the way I think of them. They list them this way, and there's a reason for that, but we aren't even at the point of me explaining what that reason is yet. Just remember that. Now, we seldom write them out like this. We're lazy. Remember, good mathematicians? A little bit lazy, okay? What we usually use is the first 3 letters of that to represent sine, the first 3 letters of that to represent cosine, the first 3 letters of that to represent tangent, the first 3 letters of that to represent cotangent, first 3 letters of that to represent secant, and then do we use the first 3 letters here to represent cosecant? Why not? We use those to represent cosine, so we have to have different ones. So we use the first 3 consonants, CSC, to represent cosecant. Okay? Now, what's more, we usually don't use cosecants that much anyway, so I don't mind having CSC. It's just, I have trouble writing it sometimes. All right, those 6 functions are normally abbreviated SIN, COS, TAN, COT, SEC, and CSC. Okay. Get used to those. I'm not going to write those out very often at all. Okay. Oh, and by the way, are any of you not able to access your ebooks if you went through Cengage Unlimited? Are you all able to access them? Any of you need a code? You do need a code. Okay. Now, I've requested the code from the company. I still haven't heard back from them. So hopefully sometime this week I'll hear from them. They usually are pretty good, but sometimes they're a bit slow. Especially, I guess, at the beginning of a term. They may get hit by this a lot. So anyway, I hope to have those soon. As soon as I do, I'll put them on Blackboard as an announcement, and we'll go from there. All right. Any questions so far? So here's the definitions, and this is the place that gives people problems later. Okay? The definition of the trigonometric functions, let t be the real number. I should say theta be the angle, but they say t is the real number, and let xy be the point on the unit circle. And that is so important here. These formulas you see down here only pertain to unit circles. Later, we'll do functions not on unit circles, and sometimes people will say the sign is y. And it's not anymore. On the unit circle it is, so that's the only place. Okay? And cosine all the way. So sine of t is y, cosine of t is x, tangent of t is the ratio of sine to cosine, which is the ratio of y to x. Hang on to that concept. We'll be using it a whole lot. But, you see, we also run into a problem here. This t, for any value t, the sine of t is y. There's no limit. Any value t, that'll be your y. Any value t, that'll be the cosine of that value will be your x. But you can't say that for here. There are some t's that you can't have values for, and that would be where x is equal to 0. Right? Because you can never divide by 0. Okay? So let's go back and look real quickly. Okay? One more. Yeah. When x is 0, tangent is not defined at pi halves and 3 halves pi, where x is equal to 0. So pi halves and 3 halves pi, and need multiple of those. half multiple of those. Well, that's not quite right either. Any half pies. 1 half pi, 3 half pi, 5 half pi, negative 1 half pi, negative 3 half pi. Any half pies, the sign, the tangent is undefined. Because there you're dividing by 0. All right. Let me get. Is it Ashton? Yes, okay, I thought so. All right, good deal. Good attending class here. Good to see it. All right. We are over here. All right. So tangent not defined at your half pies because that makes your x equal 0. Now again, I like to go down to cotangent next. Cotangent is the reciprocal of tangent, which is cosine over sine, which is x over y. But now we have to say any value t that makes y equals 0 is not allowed. Where is y 0? At your whole pies, not your half pies. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, negative pi, negative 2 pi, negative 3 pi. Yep. All those, your cotangent is not defined because the y is 0 there. Now, secant t is reciprocal of cosine t. Just like cotangent reciprocal of tangent, secant is reciprocal of cosine. Okay, 1 over x. But guess what? Again, those places where x equals 0, your half pies, secant not defined. Same places, tangent not defined. The secants are not defined because you divided by x in both places. And then cosecant is 1 over sine. See, each of these are your reciprocal identities right here. One is the reciprocal of the other. These are fine forever because you can have a 0 if it's in the numerator. You can't have it in the denominator. So cosecant not defined on your whole pies, any place where sine is 0 or y is 0, that would be your 0 pi, 2 pi, 3 pi, negative pi, negative 2 pi. So, make sense? Now, I'm going to say it now, hopefully, to help you keep from making the mistake of saying, oh, sine of t is y. That's only true on the unit circle. And here's why it's only true on the unit circle. The real definition for sine is y over r. But what's the radius of a unit circle? 1. So y over 1 is 1. Same thing here. It's x over r. So that's 1. This is r over x, but r is 1. This is r over y, but r is 1. So that's the real definition. I wish they wouldn't even say this. I wish they'd go and say r, but then tell you r is equal to 1. So for unit circle only, these are the definitions. Now, tangent and cotangent are true whenever, because you don't have the radius anywhere in that definition that you do for the other 4. Okay. So please don't fall into that trap. Okay. In the definition of the trigonometric functions, note that the tangent and secant are not defined when x equals 0, which is at the half pies, and because at t equals pi halves corresponds to the point 0, 1, follows that tangent pi halves and secant pi halves not defined. They will not have value set. Similarly, the cotangent and cosecant not defined when y is equal to 0, that's at the whole pies, at t equals 0, t equals pi. The xy point at t equals 0 is 1, 0, cannot divide by 0, so therefore cotangent 0 and cosecant 0. Totally undefined. Cannot even refer to it. Okay. Any questions? All right. And this is true for any, not even unit circle, anywhere. You still can. So, here are some of our favorite values. Okay? In this figure, the unit circle is divided into 8 equal arcs corresponding to these t values. Okay? 8 equal arcs. Well, this divides it into 2 equal arcs. This then divides it into 4. And then add these 2 and you got it into 8. So here's going to be an arc, an arc, an arc, an arc, an arc, an arc. Okay, and if these are exactly bisecting those angles, then we have exactly equal arcs. Okay, so what are the angles? They call them the t-values. Pi fourths, pi halves, 3/4 pi, 5/4 pi, 3/2 pi, 7/4 pi, and 2 pi. So there they are. 0 here, pi fourths, pi halves, 3/4 pi, 5/4 pi, 3/2 pi, 7/4 pi, 2 pi. Back here, same as 0. Okay. Now, the question is, how did they get those xy values? Just make them up? They just popped out that way? Well, if you think about it, remember I said this line has to be exactly the bisecting line of this angle here, right? Meaning this is a good old 50 degrees, 45 degree line. Does anyone remember what, if I ask you, if all this other stuff wasn't there and all we had was a line drawn through there, what the name of that function is? It has a very special name. Just this diagonal line here. Y is equal to what? Okay, first, what kind of function is it? It's not a trig function, not a quadratic function. It forms a straight line, so it's a linear function. And what's the y-intercept? 0, because it intersects there at 0. So you have its y is equal to mx. Well, what's the slope there? Okay, yeah, it is 45 degrees, but that's the angle. But what's the slope? 1! Exactly. That's called now I go blank on it. Identity function. Okay, I like to think of it as unit, and it was that. Identity function. Because whatever x value you have the same y value, right? Because that's a 45 line. That's the diagonal, okay? You go over x here, you go up y there. And they're the same length. And here and here. So now we know at this point here, the x and y values are the same, right? It's the identity function. Okay, now, because of that, because we know that x, let me get my pen set up. Okay, well, it's not setting up. Okay, there it is. X equal y. But what else do we know about x and y on the unit circle? An equation that's always true on the unit circle. The unit circle, what equation is always true?
X squared plus y squared.
Perfect. X squared plus y squared. Because x squared plus y squared for any circle is r squared, but because it's a unit circle, radius is 1, that's 1. Okay? Now, what you want to plug in for? Plug in x for y or y for x? I don't care. Name one. Second? Because x is equal to y. Okay? So I can plug one in for the other, right? Which one you want to do? X, okay? So we'll have x squared plus, instead of y squared, we'll make it x squared is equal to 1. That's true on this line, and it's true on the unit circle, so therefore it's true right there. Okay? Right? So that's the combination of this line, which is this line right here, and that circle. That's true for the circle, so therefore the point of intersection, that has to be true. Well, we can simplify that a little bit, can't we? 2x squared is equal to, and then we can do what? Divide both sides by 2. Okay? That gives us x squared is equal to 1/2. If I don't really care what x squared is, I want to know what x is, what do I do next? Take a square root. So it would be x equal to, and technically we really should say plus or minus, shouldn't we? Plus or minus the square root of 1/2. Right? Which, another way we could say that is x equal plus or minus the square root of 1 is 1 over the square root of 2. Now, a lot of times in math, they don't like having radicals in the denominator. This was from the old days, before calculators, before cell phones, before computers. If you were trying to divide this number into that, this number is an irrational number. 1.414, blah, 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 blah. It goes on forever. It's an irrational number. No pattern. The 141 doesn't look like it is, but after that, there's no pattern whatsoever. And if you were trying to get, name a number, digits, precision, pick a number. Say again. You said something. What did you say? 6?
Yeah.
Okay. 6 digits, then you need to have 1.41, 4, and 2 more digits there, rounding the last one, right? Yeah. And then you divide that into 1, then you have to do 1.0000000, 6 zeros here, move this 0, that 0. Oh, what a mess. And this is before calculators, so you can't divide either. You have to do it by hand on paper, long division, and that still gives you an approximate answer. Okay? A mess, right? But what we chose to do, multiply the numerator and denominator by root 2. Why can you do that? What is root 2 over root 2? 1. When can you multiply by 1? Anytime you want to. It doesn't change the value at all. So this gives you the square root of 2 over what? What is root 2 times root 2? 2. Ding, ding. There we have root 2 over 2. That's where it came from. Now, if you're wondering what the minus sign, that gets you down here. Because this line also intersects the unit circle down here, where it's minus root 2 over 2. Root 2 over 2. So you see both of these fit all in there. Okay, so sure enough, these 2 points are on that. And that's where the square root of 2 over 2 comes from. This operation we just did. Okay. And by the way, root 2 over 2 is about 0.707, blah, 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 blah. So you see those, expect that. All right. Now, so you could have done the same thing where y is equal to negative x, or x equals negative y. That would be a slope of minus 1, and that would be these two, and you'd have the same thing, except one of these would be plus and one minus, and vice versa. Y is equal to minus x, or x equals minus y. So then they turn out the same values, but one plus and one negative. Both plus, both negative, one positive, x negative, y positive, or x positive, y negative. So those values all the way around it. So we know not just 4 points on the unit circle, now we know 8 points on the unit circle. Any one time t is equal to pi fourths. Okay? Or 3/4 pi, or 5/4 pi, or 7/4 pi. Those are those points there. Okay. Make sense? So these aren't magic. They're not just something someone made up. You can derive these if you want to. Get to know them. They're going to be your friends. Okay? Big friends. You're going to use them a whole lot. Okay? So that accounts for every one of those 8 points there. There's 9 actually, because 0 and 2 pi are the same. 1, 2, 3, 4, 5, 6, 7, 8, 9. 0 and 2 pi are the same. So now we know those, right? Want to meet some more? Oh, let's do this. Let's divide our unit circle into 12 equal pieces. We're kind of used to this, aren't we? Good old clock, right? Now we can figure out how long each of these arcs are here, because that's 12 equal pieces. This is fourths. 1, 2, 3, 4. Divide each of those by 3. There, 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 and there. You got a total of 12 equal pieces. Pretty small piece of slices, but yeah, I can handle that. Okay. And here's what they are. 2 pi divided by 12 is pi 6. So 0, pi 6, pi thirds, pi halves, 2/3 pi, 5/6 pi, pi, that's exactly 1 pi there, 7/6 pi, 4/3 pi, 3/2 pi again, 5/3 pi, 11/6 pi, that's 1/6 pi short of 2 pi, and 2 pi, which is back exactly to that. So there, those points. Now, how in the world did they get those fractional values? You just made them up? What's that? Okay. The other was 45 degrees. These are 30 each. 30 each is 90. Okay. So yeah, thinking in degrees, that's how. But let's see mathematically why. Okay. First question is, every one of these radii are what? 1. It's a unit circle, right? Unit circle. Okay. Now, I'm going to pick one, and you could have picked any two. Pick two. Let's just say this one and that one. Okay. Now, what I'm going to do is connect the line through these two. Okay. All right. Now we know that the y value here is exactly the same value as the y value there, only this is a minus, right? Okay. Now, let me do that. Draw that line in here. I don't draw lines very well, but bear with me. Okay. Now, we know that these two lengths are the same. They're both 1. Okay. Now, we also know that those two angles are the same. They're both 1. Right? Not 1. They're pi, okay. They're pi 6. Right? This is pi 6. So pi 6 plus pi 6 is what? 2 pi over 6, which is pi thirds. So this angle here is pi thirds. What's that? Okay. We're just identified when we split this into 12 equal pieces. This will be 2 pi divided by 12, which will be pi 6, right? 2 pi divided by 12, pi 6, right? And we did this one and this one. This is just pi 6 down this way. So these two added together is 2 pi 6 to 2 pi thirds. Right? Now, I want you to note something. This angle here, whatever it is, has to be the same as that angle there, right? These angles are the same. That splits it exactly. So this has to be the same. So here we have a pi thirds plus 2. Let's give them names. Theta, okay with you? Okay. So we know those two are the same. So we know that pi thirds plus 2 theta. And what's the sum of the 3 angles of a triangle? 180, but I'm dealing with pi's here. So how many? 180 degrees is how many pi's? You better remember that. 1 pi. So that's equal to pi. Okay, I want to know what these two angles theta are. See, this is angle theta. That's an angle theta. Okay, so I want to identify that. So what do? Solving for theta. Yeah, subtract pi thirds from both sides. So minus pi thirds, and that will give me, that goes to 0, 2 theta. And what if I subtract pi thirds from pi? What do I get? How many thirds is pi? 3 thirds. Minus 1 third is 2 pi over 3, right? 2 thirds pi. Divide both sides by 2, and what do we get? Theta is equal to pi thirds. Hey, wait a minute. All 3 of those angles are the same. If this angle is pi thirds, and that angle is pi thirds, and this angle is pi thirds, what kind of angle triangle do we have there? Equilateral. Equal lengths, that's what equilateral means, and equal angles. Right? So therefore, what's the length of this? 1, because this length was 1, that length was 1. But if that's 1, and this exactly the same length above and below here, what's this length here? 1/2. Looky there, there's a 1/2. That's how we came up with that. And this is minus 1/2 because it's below the x-axis. Okay? So, we now know the y value of this point here. We don't know the x value here. How can we figure it? Is there any way in the world? What's true about every point on the units? You got it. X squared plus y squared is equal to 1 because it's on a unit circle. Okay, it'll come back. Every time I move the screen here, it blinks in and out. Okay, but we already know what the y is, so this will be x squared plus, and what was our y again? 1/2. And 1/2 squared is 1/4. So this will be x squared plus 1/4 is equal to 1. So guess what x squared is? Say again? Anyone do that in your head? 3/4. Okay. Just think of money, $1. X squared plus $1 quarter would be $1. So x squared must be 3/4. Okay. Got it? Okay. Never mind. And now what do we do? Square root of both sides, and that would be x equal, technically plus or minus, the square root of 3 over 2. And look what the x is. Square root of 3 over 2, or minus the square root of 3. No, here's the x. Sorry, I circled the wrong one. It says square root of 3 over 2 because x is positive on both of those. So let me erase that. Okay. Got it wrong. Okay. Circled the wrong one. But if you went on the other side over here, that's where you minus square root of 3 over 2 is. So here we know what this point is. The x is square root of 3 over 2, the y is 1/2. That's on the unit circle, and that gives you an angle of pi 6. A t value of pi 6. You double this, and you move up here. Well, now you can do the same thing up here and find out the x is 1/2, and the y would have to be square root of 3 over 2. And then over here it's minus 1/2, positive square root of 3 over 2, minus root 3 over 2, positive 1/2. Everything is symmetrical out there. So we have every one of these. So before we had 8 values. Here we have 12 values. A few of these are common. This one, that one, that one, that one, that one are common to both. But now we have a whole bunch of points, and we know the angle, the t value, and we know its coordinates. Get to know them. These are, yes?
I got how you got the coordinates. How did you get the t value?
The t value is what I was calling the angles. These are your t values. See, corresponding to the t value line. And the reason is what they do with the t value. Imagine doing an axis, a y-axis, only it's a t-axis over here, just like this, and wrapping that around the curve, so that's your arc length. Remember, on the unit circle, or on any circle, s is equal to r theta. On a unit circle, r is 1, radius 1, so s is equal to theta. So only now we're calling the s's t's, so t is equal to theta. So what I've been calling thetas here, they're calling t's. It has the same value. It's just t. When I think of t being a length, I think it has some dimension associated with it. Here they say, no, it's a dimensionless quantity. Why don't we just call it theta then? I call it t, because it is actually an angle. But I'm not going to argue with them. This is how they teach it. So, and everybody uses that same value, t value. Think of them as the thetas. Same value on the unit circle. Not a unit circle, then you would use thetas, and it would be exact. Okay. All right. And here goes into how we did it. I'm not going to go through this again, but to verify the points in that first figure, the root 2 over 2 also lies on the line y is equal to x. That's exactly where we started the identity function, y is equal to x. Substituting x, y, and here we went back and got exactly the same thing. And here's root 2 over 2 and minus root 2 over 2. Those are the x values, and the y values are the same, so they're root 2 over 2 minus root 2 over 2 because x is equal to y. and then you can do the -1, and x is equal to -y, and they work out the same. So when x is root 2 over 2, y is minus root 2 over 2, when x is minus root 2 over 2, y is positive root 2 over 2. So there's those, and let's see, are they going? And in the first quadrant, they're both positive. That's the only thing at the bottom to say. All right, and then similar reasoning to do this, and they just don't tell you what the similar reasoning is. I showed you what the similar reasoning is using equilateral triangles, which you have to prove to yourself, convince yourself those are equilateral triangles, and indeed they are. Okay. And it says example 1. Demonstrate that procedures. So let's see what example 1 is. All right. Let's evaluate all 6 trigonometric functions at each real number. The first one is going to be at t equal pi 6. So what I'm going to do is the sine of t, the cosine of t, the tangent of t, the cotangent of t, the secant of t, and the cosecant of t. Okay? Now, in order to do this, what we have to do is remind ourselves what are the xy values corresponding to t equal pi 6. That's what you have to do. First, find where you are, Waldo. Okay? Where are you on that unit circle when t is equal to pi 6? What point are you at? XY point.
X is 3 over 2,
Okay, the x value is square root of 3 over 2. Y value was 1/2. Is that what you said? Perfect. Okay. Now, remind me what the radius is. 1 is a unit circle. Okay. And what's the sine of t? Yeah, it's the y value. It's really y over r. I'm going to keep saying that so you won't mess it later. So this is going to be 1/2. What's the cosine t? Pretty exciting, huh? What is it? It's the x value, square root of 3 over 2. And what's the tangent of t? Y over x. Now this is why I write them this way, because now you can just do a line like that. Okay? I'm really lazy, you see. Y over x. And now you see the 2's go out. You multiply both numerator and denominator by 2, and you get 1 over root 3. But if you don't like having radicals in the denominator, what would that be? Root 3 over 3. Perfect. All right? And then what would cotangent be? I go around like this. It's reciprocal of tangent. So go back to this one and reciprocate that, and what do you get? Root 3 over 1, which is just root 3. Perfect. Okay? And then for secant, what would you get? Remember I said you reciprocate the cosine. That's why I put it next to it there. What does that become? 2 over root 3, but if you didn't like radicals in the denominator, you could write it as 2 root 3 over 3. Perfect. Okay? And then, I never finished the rest of that story. Now, remember when I was talking, let's finish this first, then we'll come back to it. And what would cosecant be? 2. Perfect. Okay. Now, I want to point something out to you. Okay? Okay, I want you to think of angles, lengths of sides in radian. Okay? The length of either one of these sides, the horizontal side or the vertical side, is always less than or equal to the radius. Right? This is the short side, that's the short side, this is the long side. The hypotenuse is always the long side, right? So therefore, since this is y over r, it doesn't look like it here, y over r, then this is always less than, or occasionally equal to 1, but never greater than 1. Same with the cosine. That's the x over r. Always less than or equal to 1. Okay? Tangent can be anything. It can be huge or it can be tiny. Okay? No restriction on tangent or cosine. But secant, because this is always between basically -1 and 1, this is always outside -1 and 1. You'll never have a secant of be 0.7. Ever. You could have a sine or a cosine 0.7. You'll never have a secant. This is always going to be a number greater than 1 or less than -1. Cosecant, same thing. Okay? Just for future reference. Don't ever give me a sine or a cosine of 3.4. Can't happen. It's got to be less than or equal to 1. And therefore, secant and cosecant, don't give me a secant cosecant -0.3. It can't happen. It's got to be -1.3 or, it's got to be bigger absolute value numbers than 1. These have to be absolute value numbers less than or equal. Just for future reference. You don't have to think of that now. Okay, but what I was telling you before, remember when I was talking about, I got distracted when we were doing 1 over root 2, and remember I said this would be 1 over 1.414, blah, 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 and if you're dividing that, it would be 1.414, blah, 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 divided into 1.00000, and you had to do it long division. Remember that nightmare, of doing that? This is way before computers. Okay, now let's write this as root 2 over 2. Root 2 over 2. Same value, right? And that would be 1.414, blah, 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 divided by 2. Well, I can do that in my head. 0.707, and whatever numbers were, I can keep dividing. In my head. This one, long division, not in my head. Nowhere close. That's why in the old days, they always rationalized denominators to make division easy. Okay? And easier. Okay? If you had radicals in the denominator, you have to find out the value of that to the amount of precision you're interested in, maybe even going one more digit, then do a long division, which is really a headache and a half, and then rounding that answer. Oh, what a pain. So always rationalize the number. That's why they used to do it. Nowadays, when's the last time you did long division, huh? Did they teach it in grammar school maybe? That's probably it. Calculator ever since? Just about, right? So nowadays, there's really not the need for rationalizing, but they still do. Mathematicians get to be, like everybody, stuck in a rut. But we did these 6 values. Let's move to the B part. Now, I've written all over the page, but I'm going to oh, I did too much. This was all extra, but no extra charge, by the way. Okay, all covered by your tuition. Okay. I lost a C in there, didn't I? Let's do it for 5/4 pi. T is equal to 5/4 pi. Where are we, Waldo? Okay. We're in the which quadrant? Third quadrant. So the x value you said was minus, did you say root 3 over 2?
Root 2 over 2.
Oh, yeah, you're right. Root 2 over 2, because this is 1/4 pi. And this was also negative root 2 over 2, because both are negative in the third quadrant. Okay? So now it's sort of a piece of cake to do this. What's your sine of t? Negative root 2 over 2 over 1, which doesn't change the value any. Cosine of t is negative root 2 over 2 over 1, which doesn't change its value. And then what's tangent of t? And what is it? What value? 1. Exactly. Negative by negative is positive. Root 2 over 2 over root 2 over 2 is 1. Okay? That's it. Okay? Cotangent of t is 1 because it's reciprocal of tangent. And secant of t is what? Now, in this case, I'm going to go backwards. Okay? Let's go back and write this, what it was before we rationalized its denominator. What was that? One over root 2, negative 1 over root 2. So now it makes it easier to take the reciprocal of that. And what would that be? Negative root 2. And guess what cosecant would be? Negative root 2. Perfect. See? You got all 6 of them just by knowing your coordinates. And that's where you begin. Figure out what coordinates represent that t value, or that angle. Okay. That was pretty easy, wasn't it? Somewhat. Okay. Any questions on it before I erase it? Okay. Then let's do, I'm going to be really lazy this time. Okay. All right. T is equal to pi. Negative 1, 0. Got it. So what's your sine t? Sine of pi? Someone said 0. Cosine pi? Negative 1. Tangent pi? 0. 0, negative 1. That's why I left the line there. So what's cotangent t of pi? Say again? Undefined. Okay. What's secant of negative of pi? I was just giving it away. What is it? Did someone say it? I thought I heard someone say it. Negative 1. Perfect. Okay, I thought that's what I heard, but I wasn't sure. And what's cosecant of pi? Undefined. Perfect. Okay. Now, here, one of those rare cases where cosine of t is minus 1, but secant t is minus 1. Remember I said cosines and sines have to be between plus or minus 1, but they can't actually be plus or minus 1. This is minus 1. So when cosine is minus 1, then secant is also minus 1. And when sine is 1, then cosecant is 1. I mean, they're going to have the same values there. But any other time, these are going to be less than 1, between minus 1 and 1, and these are going to be outside. Just for reference. Okay. Now let's do the last one. Woo, I braced too much. All right. Now we have t is equal to negative pi thirds. Where are we now, Waldo? Fourth quadrant. Okay, so what are our coordinates there? 1/2 and negative what? Root 3 over 2. Okay, let's think about this a moment, make sure we're right. Yeah, the negative pi thirds is going to be an angle down like this, so you're only halfway on x, but you're almost down to minus 1, which is minus 3 over 2 on y. So yeah, that seems right. So now can you write down what sine of negative pi thirds is? Negative root 3 over 2, because it's the y value over 1, which is the y value, and cosine of negative root 3 pi thirds, negative pi thirds is 1/2. Tangent would be negative root 3. See how Writing it this way makes it so easy. But then what would cotangent be? Negative root 3 over 3. Negative 1 over root 3, which is reciprocal of this, which then to rationalize that gives you root 3 over 3. Good. How about secant? What would that be? 2. And what would be cosecant of negative pi thirds? Give it to me in a simple way first, and then we'll change it. Negative 2 over root 3. That's one way, and if you don't like having radicals in the denominator, that would be negative what? Negative 2 root 3 over 3. Perfect. 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 My goodness. I wish I could figure out a way to make it harder. This is so simple, but I can't. So we're stuck with this. Okay? Make sense? Yeah or nay? I'm sort of being a little facetious, but it sort of just pans out, doesn't it? Okay. Get to know those favorite angles. 0, pi thirds, pi 6, pi fourths, pi thirds, pi halves, and all around like that. Okay. Ooh, I didn't flip the page. That was example 1. By the way, every example is followed by a checkpoint, and the checkpoints I would do as soon as I could after you get out of class, not to interfere with another class. As soon as I could, try to go back and do the checkpoints. They're very, very similar to what your example was, and that way you are not spectating watching me or someone else do it, you're doing it yourself. And if you can't remember how we did it, audio video solutions are at larsonprecalculus.com. You don't need a code for that. Anyone can go to that website. You'd have to know how to navigate it, but I think y'all can figure that out pretty easily. All right, any questions on that? Oh, let's see how they do it. I'm sorry, I forgot. This is one here, so let's erase all this. Let's do it first. For each t value, begin by finding the point. Figure out where you are and what the xy coordinates of that point are on the unit circle. Once you have that, you can write down the trig functions. That easy. At pi 6, that corresponds to being on the x, you're almost to 1, root 3 over 2, and you go up 1/2 on y. So there's your xy coordinates. And once you have that, the sine of this is the y value, the cosine of this is the x value, over 1, of course, okay? And the tangent is the ratio of those two, and then all the rest are reciprocals. So it's pretty simple to do. The sine is pi 6 is your y over 1, because remember that is over the radius, which is 1. And that gives you 1/2. The cosine is the x value, which is root 3 over 2. And the tangent is the y over x, which is basically just divide those, and you have 1 over root 3, which comes out being root 3 over 3. Okay. Now, they then go to cosecant. I go across the page and do cotangent. Next, they do cosecant. So we'll jump back up the sine and first do cosecant is 1 over y, or radius over y, and that's going to be 2 over 1, 1 over 1/2, which is 2. Secant would be the reciprocal of the cosine, which is root 2 over root 3, which comes out being 2 root 3 over 3, and the cotangent is x over y, which is root 3 over 2 over 1/2, which is simply root 3. Good deal. Any questions? All right. And since I told you a little bit of things to remember about sines and cosines always being between -1 and 1, so therefore secant and cosecant are outside that. If tangent is between -1 and 1, then cotangent's outside of it. And if sine tangent is outside of -1 over 1, cotangent is inside of it. They're reciprocals of each other, so if one's big, the other's small. Okay. All right, the b, then we go to t is equal to pi force pi, and as I believe it was Patrick said, that point is minus root 2 over 2, minus root 2 over 2. Third quadrant, everything's negative, and you're quarter pi, so you're root 2 over 2s. So it's minus root 2 over 2, minus root 2 over 2. The sine is the y of that, which is minus root 2 over 2. The cosine is the x of that, which is minus root 2 over 2. The tangent is the ratio of those two, which comes out being minus root 2 over 2 over minus root 2 over 2, which is 1. Okay. Then I like to go on and do tangent. They jump up and do cosecant, and that would be, but remember where that y came from? It used to be minus 1 over root 2, so reciprocate that, and you get, this is the long way around to do it, negative root 2. And then the secant, which is going to be the reciprocal of cosine, and those have the same value, so it's going to be the same value, which is minus root 2. And then the tangent, cotangent, it's going to be reciprocal of tangent, and that's just going to be 1. Got it. All right, then for t equal pi, we're over here at negative 1, 0. So sine is going to be the y value, which is 0. Cosine is going to be the x value, which is minus 1. But remember, it's y over 1 and x over 1. That's going to be your minus 1. And the tangent is going to be the ratio of those, which is 0. We'll get back to it later. The cosecant they do next is, guess what? 1 over 0. 1 over sine. Can't do it. Undefined. Perfect. And cosecant of pi would then be 1 over x, which would be 1 over negative 1, which is negative 1. And then the cosecant of x of pi is the y of x over y, which is negative 1 over 0, totally undefined. All right, good deal. And the d, moving clockwise now down to minus pi thirds, you're down there at the x value minus 1/2, the y value, positive 1/2, y value negative root 3 over 2. And the sine is the y value over 1, which is negative root 3 over 2. Cosine is the x value, which is 1/2. And the tangent is the ratio of those two, which is negative root 3. All right. Then they go up to cosecant, which would be the reciprocal of that, which would be negative 2 root 3 over 3. There it is. The secant, which is 1 over the cosine, the radius over the cosine, and that would be 1 over x, radius over x, and that would be 1 over 1/2, which is 2. And the cotangent is the reciprocal of the tangent, x over y, which is 1/2 over that, which is negative 1 over root 3, which you can then could write as negative root 3 over 3. Done. Any questions? All right. And there's a checkpoint, so remember to do the checkpoints. All right, now we're going to look at domains and periods of sine and cosine. Okay. Now, what do we mean by domain? Yeah, all the input values you can do to the sine and cosine. And guess what they're going to be? All real numbers. You can put them in because there's no limit on sine and cosine. Okay? Now, the period of sine and cosine. That's something we haven't dealt with directly, so let's take a look at it. The domain of the sine and cosine functions out of all the real numbers, positive and negative, and to determine the range of those two functions, and this is what I've been talking about before, the domain is where you can go along the circle. You can go round and round and round and round, infinitely number, or negative, round and round and round, no breaks, no nothing. So yeah, domain is all real numbers. Okay? The range, though, is always going to be between plus or minus 1 for the y. That's going to be the range for your sine function, and the range for the cosine function, or plus or minus your x, plus or minus 1. So now, remember, you can have the extremes, minus 1 and plus 1, and here minus 1 and plus 1, and every number in between, but no numbers outside of that. So never, ever, ever give me an answer, sine of something to be 1.7. It will never happen, or negative 3.5. It will never happen. They always are going to be between minus 1 and plus 1. It could be minus 1, it could be plus 1. There will always be a number in between those two, or those, same with the cosine. That's what the x's are limited to that. The domain, the input for those, the t, any real number in the world. Okay? Now, that's your domains and ranges, but we haven't talked about period yet. Okay. But we sort of have. Okay? If you think about doing this for any t value, the t can go from 0, pi halves, pi, 3 halves pi, 2 pi, but then it starts repeating itself, right? And repeating itself, and repeating itself. So the period over which it repeats is 2 pi for sine and cosine. Okay? I may have jumped a little bit ahead. I did. I'm sorry, they're back on the limits there. By definition, the sine of t is y, the cosine of t is x, because xy is on the unit circle. You know that the y stays between plus or minus 1, the x stays between plus or minus 1, so the values of sine and cosine all also range between plus or minus 1. This is just saying the same thing we were looking at before. Sorry. Do that. And then adding 2 pi to each value of t on the interval, this is what I was just talking about, results in a revolution around the unit circle, so you get the same value. So here, if you start here at 0, go up to pi fourths, pi halves, 3/4 pi, pi, 5/4 pi, 3 halves pi, 7/4 pi, then you get here to 2 pi, now you're at this one, then this will be 9/4 pi, which would be 2 pi plus pi fourths. This will be 10/4 pi, which would be 5 halves pi. That would be pi halves plus 2 pi. You just keep going around and around and around. You're the same place, same values, but you're just adding 2 pi all the way around. And then pi to 3 pi is adding 2 pi to it. You can show that here. But then everything is adding 2 pi. Or subtracting 2 pi. So the period, same values start repeating themselves every 2 pi around. So that's your period, 2 pi. That's what they're getting at. Okay? All right. The values of sine of t plus 2 pi and cosine of t plus 2 pi correspond those to sine of t and cosine of t. Because you're at the same point on the unit circle when you're t plus t or t plus 2 pi. You're right back at the same place. So the sine and cosine values, because it's the same ordered pair there, they're the same values. Similar results would be repeated revolution, positive or negative. Every time you go around, you're adding or subtracting another 2 pi. That leads to the general result, sine of t plus 2n pi. I like to say, they say 2 pi n. Later they'll say 2n pi. It doesn't matter. Just n is any integer. 1 it would be 2 pi, 0 it would be 0. Negative 1 it would be minus 2 pi. 17 would be 2 pi times 17, 34 pi. Huh? What's that? What if you forget the n? Then you're endless. Okay. I'm sorry. I didn't say that. Okay. No, if you're expressing this, you need to put that value in there. And, you'll do it often enough, I think you won't forget it. But yeah, it doesn't mean anything. You mean if you just put t plus 2 pi? That is true, but it's also true for 4 pi or 7 pi. I'm sorry, not 7 pi. 10 pi, or yeah, it has to be in some integral value. Okay.
Oh, okay.
Yeah,
I get
you
what
just go around and around and around and around. But every time it's 2 more pi, 2 more pi, 2 more pi. So the number of times around, that's your n. Okay. And for any integer n, positive or negative or 0, and real number t. The functions that behave in such a fashion, you then say they're repetitive or cyclic. They're also called periodic functions. And all of your trig functions are periodic functions. Sine and cosine especially, we use those all the time. And the period is whatever that multiple is, 2 pi. Okay. How are we doing? We're almost out of time, aren't we? Have 1 minute? Okay, let's do this one then. A definition of periodic function. A function f is periodic when there exists a positive real number c such that f of t plus c is always f of t. In other words, whatever you add to it, it's going to come out the same value. That's what a period. For all the t in the domain of f, the smallest number c for which that is periodic is called the period of f, and for sine and cosine, that's usually 2 pi. Now, we also know the even and oddness thing. When f of minus t is equal to f of t, we call that an even function. Because you go to minus t here, go positive t there, if you get the same result on either side, that's an even function. But it's odd when f of minus t is exactly the opposite of f of t, then that's called an odd function. So sine and cosine, cosine and secant are even functions, okay? And sine, tangent, cosecant, and cotangent, the reciprocals, are all odd functions. They just threw that one in there on you. So that's the bottom of page 273. We will start next time with example 2. So probably I should have stopped while the starting was good, but I didn't. Okay. Now, before we go, let me give you some homework exercises. I know you don't want to leave home without them, or leave here without them. You can do any of the odds, either 5 or 7. They're both at calcchat.com. Either 9 or 11. They're both at calcchat.com. Then do any of the odds, 13 to 21. They're all at calcchat.com. Any of the odds, 23 to 29. They're all at calcchat. 23 is at calcview. Any of the odds. Let's stop there. We'll stop there at 29, and we'll pick up the rest of those later. Good deal.